All right, well, welcome to the first video that you're going to be watching about the theory of the electronics lab. So again, I like doing it this way for these online classes. You get all the theory out of the way, and then when we come to actual class on Tuesday, we can go through some examples and we have more interaction. You can ask me a bunch of questions. But this way, go through the video that you're about to see, pause it when you need to, make some notes. That's the way you should be doing this. So what we're going to do today, theory for this week, is Ohm's law, resistance and voltage dividers. So some of this, hopefully you've seen before in physics class, at least hopefully some of this first little bit of material. So it should be some review. So if you don't need to take notes on that, it's fine. When it gets to stuff you don't know, that's when you should be taking notes. So current and voltage, electricity, caused by the flow of electrons. That's due to some potential difference, some voltage source. So if I have two conducting parallel plates at a voltage source from a battery that charges one plate to a positive potential, charges the other one to a negative potential, that's then going to influence these electrons. The electrons being negative charges, they're attracted to positive charges, so that's going to make them go over to this guy and away from the other negative charges. So that flow of electrons causes the current. These two oppositely charged plates cause an electric field. So the force on this charge Q is related to the electric field just by simple multiplication. Electrons all have a charge of negative 1.6 times 10 to the negative 19 coulombs. So electrons, again, being negative. Electric field is related to the voltage source, so whatever the battery voltage is divided by the separation between the plates gives me that strength of the electric field. So again, that's also related to the force. And just set up here, I have two parallel plates, oppositely charged. Probably heard of those things before. That parallel plates gives you a hint. Parallel plate capacitor. So again, I'm going to have some acceleration based on this force, based on the electric field or the voltage and the length. That's also going to give me some kinetic energy. So again, this charge here is going to be accelerated to some speed, and that speed is related to potential energy. And then what current is actually these charges moving. So current is a measure of how many charges or how fast these charges are moving, depends on the way you look at it. It's basically how much charge, how much total charge is passing through a certain point at a given time. So if I have a whole bunch of electrons or a whole bunch of charges, some charge Q moving between the plates, my current is that total charge, so the total number of charges of those certain charge values. So again, that's my total charge moving through some point. And that's generally measured in amperes or amps, which are coulombs per second. And so based on this, based on the fact that I know that 1 amp, what I'm looking for, and then the charge of a 1 electron is 1.6 times 10 to the negative 19 coulombs, the total number of electrons flowing past a certain point to give me 1 amp is 6.25 times 10 to the 18th electrons per second. So that's what 1 amp of charge is related to how many electrons are going through your wire or electric circuit or whatever it is. So voltage is what actually makes current. So without a voltage difference, without a different charge on my two parallel plates, there'd be no reason for those electrons to move. So voltage is the driving force behind any sort of current. So in a sense, voltage causes current. And voltage could be made from many sources. So there's electrochemical reaction. That's what happens in batteries. So in batteries, you have some chemical in there and they interact with each other, giving you a voltage. Electromechanical system. So this is kind of how your household electricity is generated. You have something, basically a big magnetic field that's moving, and changing magnetic fields causes electric fields, and that causes electrons to move, gives you current. So that's a voltage source. There's also some direct conversions, so solar cells, which are also called photovoltaics, and other things as well. And voltage is one of those relative things. So voltage many things in physics kind of have this arbitrary 0 point. Voltage is one of them. And so the arbitrary 0 point we usually use for voltage is what we call ground. It's kind of the voltage of the earth. So pictorial form, you have some conducting material, some ground rods into the earth, and that's where all my negative. So negative is essentially 0. So negative voltage is my ground voltage, that's 0. And then my positive voltage is whatever I have. So if my battery is 5 volts, then that's what my positive voltage is. So again, some negative terminal attached to the ground, same thing with the battery. So the negative side of my battery is grounded. It's at this reference value of 0, meaning that my positive side is that full 5 volts or whatever it is for my actual battery. It could be 12 volts, could be 1.5 volts, whatever it is. So in terms of the actual current, there is a convention as to which way current actually goes, and that is that current goes from the positive side of the battery to the negative side of the battery. However, as I've been saying, it's always these electrons that are moving, and so it's really the electrons that are moving away from the negative side and going towards the positive side. So if I look at my actual little circuit here, I have this battery, positive on top, negative on the bottom. What's really happening is the electrons are leaving this bottom surface because they're being repelled from the other negative charges. They're being attracted to the positive charges. And because this is a conducting wire, that's the way they want to go. So they go out of this negative terminal to the device into the positive terminal in this counterclockwise manner. However, by convention, this current is actually moving in the same direction as the positive charges. In other words, the current is actually moving in the clockwise direction. So that's just by convention. Really what's happening is, again, the electrons are moving. The positive charges don't actually move. The positive charges are bound to the nucleus in the atom, so they actually can't move. It's only electrons in the outer shell that can actually move around. But by convention, well, we always go with a positive charge. So you can think of a negative electron flow as being positive, so kind of two negatives make a positive. So a negative direction of the electrons is the positive current direction. And then how much current you actually have is related to voltage, but it's not just related to voltage, it's also related to what's happening in this actual device. So we'll see that a little later. A lot of times you see circuit diagrams, so the little one we had before. So this is a very simple circuit diagram. Here's a more complicated circuit diagram. I have some 120 volt AC source. That's basically what comes out of your wall. Have a transformer, have a Wheatstone bridge diode filter configuration. Rectifier configuration. The filter sees this capacitor and resistor in parallel. And so this more complicated circuit diagram, that's actually something you're going to see in, I think it's lab 3, you see something like this. And so you're actually going to build one of these and measure some properties of it. But you can see the whole wide range of symbols here. There's these weird curly things, little triangles, capacitors, resistors. And so we have little symbols for all these different devices that you'll see a lot of, and you probably have seen some of them, maybe haven't seen other ones. But again, what you want to have to do with this is take this diagram and actually put it onto your breadboard. So actually put your proper components in the proper places to make this same thing happen. Essentially, these circuit diagrams tell you which way kind of current flows. So most of these things, the wires hooked up to this transformer, hooked up to these diodes in a certain way so that the current can flow which way it's supposed to go. From these points into the capacitor, so that these points are connected to the right places in your actual breadboard. So that's kind of part of your lab this week, is to actually be able to translate these into actual circuits. So again, many of these symbols have transistors, have LEDs, also other types of diodes, direct current sources, ACs, current sources, switches, op amps, we'll see those week 4, I believe. Some inductors and transformers. Transformers are essentially 2 inductors, so that's why it looks like that. Capacitors, you have your normal capacitors and your electrolytic capacitors. So these guys have to be careful because if you hook them up backwards, they blow up, and I have seen that many times in lab. Resistors, again, a few different types of those. So these are just the kind of more common ones, are the ones that we'll probably be seeing most of in lab. I don't think there's too many other than this we'll see in these next 8 weeks, but there's a whole bunch of them. Front cover of your book has a ridiculous amount of them that you could possibly see. So going back to what I was saying before about the electrical conductivity. So again, you see the electrons that move. For good conductors only have a couple electrons in their outer shell. There's only a couple electrons in the outer shell. It's really easy for those guys to break away. And so something like copper is a really good conductor. That's why a lot of wires are made out of copper, because these electrons can kind of fly off of their individual atoms. And once they fly off of their individual atoms, they can move around. And of course, negative charges moving around is what gives you current. And so that easy process of creating current means that this is a good conductor. And as it flies off, it repels other guys, and then they all kind of move in the same direction, again, giving you current. On the other hand, if you have an insulating material, glass, ceramics, things of that nature, these electrons don't move very easily. It's very hard to make them move. And so because they don't move very hard or very easily, they obviously don't move very much. And so if they don't move very much, there's not much current, because again, the more motion there is, the more atoms are there, the more electrons are that are moving, the more current there is. So that's kind of the microscopic definition of conductors versus insulators. Yeah. That's where it should be. So Mr. Ohm, way back when, found there's a direct proportionality between voltage and resistance. Famous formula, V equals IR. So your voltage is proportional to the current, and it's proportional through this proportionality constant called the resistance, capital R. And so because of that, resistance is measured in ohms. Ohms is the same thing as a volt per amp. A volt is some combination of meters, kilograms, coulombs, same thing for amps. So another way to get ohms is joule second per coulomb squared. So an amp is a coulomb per second, which means a volt must be a meter squared kilogram per second squared coulomb. So again, it all works out to joule second per coulomb squared. Now the resistance is basically related to three things. If I have electrons in a certain object, usually we have the object as a cylinder because wires are generally cylindrical. And that's usually what we talk about in electric circuits. And resistors are generally roughly cylindrical, so you usually have a cylindrical shape for our resistors, so resistance related to the resistivity. So resistivity is basically a measure for the material itself. As I mentioned before, this kind of is how easy it is for those electrons to move. We saw for copper, it's very easy, which means that the resistivity is really, really low. So again, the lower the resistivity, the easier it is for the electrons to move, the better this material is as a conductor. So copper has a very low value, iron, silver, platinum, all very low values. So again, generally metals have very low values. And then things like glass, silicon, polyethylene, mica, these are your more insulators. So again, glass 10 to the 12th, so really high value, really hard for those electrons to move. So really high resistance in glass, in mica, and polyethylene. So that's only one thing it depends on is the material. Other things it's going to depend on is the length. So the longer this tube is, or the longer the wire is, the more resistance it's going to be, because you have to go through that material for a longer period of time, essentially. So obviously, the longer it is, the more resistance there is. You can see that in the formula, L being on top, the higher number that is, the larger your resistance is going to be. But then it also depends on the cross-sectional area. So again, this is kind of like a tunnel or a pipe. The bigger the pipe is, the more water can go through it. Same thing here, the bigger the wire is, the more electrons that can pass through. And so because of that, that's less resistance. So area on the bottom. That's why you're going to see when you pull out your resistors in lab, the bigger resistors in terms of actual physical size actually correspond to the smaller values of resistance. Your 100 ohm resistor is going to be much bigger than your 10,000 ohm resistor. And resistivity measured in ohm meters. That's the way the units work out to give you resistance in ohms. American wire gauge sizes. So again, this is generally for copper wire. Wire gauge, the bigger the number, the smaller it is. So you can see the 24 gauge wire has a diameter of 0.02 inches. That's really small. 10 gauge wire is 0.1 inches, so basically 5 times bigger. And obviously, bigger diameter means less resistance, as you can see, either per 1,000 feet or per 1,000 meters. So again, based on the resistivity of copper, the diameter turned into a cross-sectional area, 1,000 feet or 1,000 meters. Basically plug that into this formula, and that should give you those numbers. So with many types of resistors, we're mainly going to be dealing with a couple versions of them. So mainly we have fixed resistors, and those are generally going to be the carbon film type or the metal film type. So you're either going to have bluish ones, which are called carbon film resistors, or you'll have beigeish ones, which are the metal film resistors. They pretty much act the same way, it's just what they're made out of. Then a couple other ones you're going to see. This week you'll see potentiometers. So these are variable resistors. You can turn this knob, and that actually changes the resistance. We'll talk a little bit more about those later. And then you'll also see some thermistors. That's in week 6. So these are variable resistors. Their resistance actually changes with temperature. So we'll see some of those. For the most part, resistors have this symbol. So that's what you'll see for the carbon film and the metal film resistors. Potentiometer, there's sometimes an arrow pointing at it, because again, you can change this. So it's kind of like the arrows changing the resistance. So my common resistors, my carbon or metal film resistors, blue or beigeish ones, you have some wire, so that's where you hook it up to both ends of your circuit. So hooked up to one end of the circuit, hooked up the other end of the circuit, then inside your kind of beige or blue encasing, there's a carbon or metal film spiraled around. And again, that's the length, the cross-sectional area of all this is kind of there to give you the proper resistance. So it knows what this is made out of, it knows its resistivity, knows its length, knows its cross-sectional area, and then that is all calculated to give you the proper resistance for this entire resistor. Then of course an insulated coating, so that if you touch it when it's live, which is never a good idea, but if you do, it may not hurt. For the labs we'll be doing, we're only dealing with about 5 volts, so you probably could get away with touching these when current is live, but you really shouldn't. Good lab practice is once the voltage is on, you do not touch the circuit. Do not touch any part of your circuit. If you want to touch your circuit, you want to play with stuff, you turn it off first. Then you change it around, then you turn it back on. So again, there's many subtypes of resistors. In certain countries, Rashi have different symbols as well, but we'll stick to this one that we've seen. And again, the only other one you're probably going to see is this adjustable one. So potentiometer, again, has this little arrow kind of indicating that it is adjustable. It's not the fixed value of the resistance. So for your resistors, you can see many of them look the same. So here's a blue carbon film one, some beigeish metal film ones. So generally all look the same other than, again, their size. So again, based on the length and cross-sectional areas, generally your bigger ones are your smaller values. So these guys have probably a lower resistance than this little guy down here, just based on the cross-sectional area. Even though the length is smaller as well, the cross-sectional area is a lot smaller. So I would guess this guy is probably 100 times the resistance of these guys, just guessing. But again, they look very similar. And so how do you know exactly what the resistance of these guys is? And the way you do that is with all these little color bands, all these little stripes. So you see all these have a bunch of stripes on them, and those stripes essentially tell you what the resistance is. So in general, there's 4 bands. These metal film ones sometimes have 5 bands. Sometimes you only see 3 bands on them. We'll get to those differences in a minute. But generally, 4 bands is what we'll see. So you have 3 bands tightly packed together, and then you have one that's kind of separated. And this one that's kind of separated is usually either gold or silver. So your first band is basically your first number. Second band is your second number. Third band is called the multiplier. And then the fourth band is called the tolerance. Again, if you don't have a fourth band, it means the tolerance is 20%. If you have silver or gold, silver is 10%, gold is 5%. So usually we have gold bands there. The blue ones usually have a different color, whatever 1% is. This will tell me what 1% is. Usually have a brown one there. So the metal ones usually have a brown as their last value. And how to read this, again, there's this table here. So every band basically corresponds to a color. So black is 0, brown is 1, red is 2, orange is 3, all the way up to violet, which is 7, gray is 8, white means 9. So each color means one of those numbers. I generally remember this because it goes black, brown, then the rainbow. I generally don't remember gray and white, mainly because I don't think I've ever seen gray or white bands in all my years of doing this. I've only ever seen black through violet, so those are the only ones I remember. But if you ever do come across gray or white, it's 8 or 9. So again, how do you read this? The first band is the first number, second band is the second number, third band is your multiplier, and then last band is your tolerance. So if I'm looking at this guy here, I have a brown stripe, a black stripe, a brown stripe, and then gold means 5%. So brown is 1, black is 0, so that gives me a total value of 10. And then my multiplier, I'm essentially multiplying by 10 to this power. So 10 to the power of 1 for brown, I multiply by 10. So I have 10 times 10 gives me a total resistance of 100 ohms. So again, I have brown stripe as 1, black stripe is 0, and then times 10 to the brown stripe being 1. So 10 times 10 to the first power, I get 100. And then with the 5% tolerance, meaning that this resistor is anywhere between 95 and 105 ohms. So it's not exactly 100, it's somewhere between 95 and 105. That's what kind of the manufacturer is going to guarantee you. So now we get to the fun part, how to actually analyze the circuit. And we're not going to be analyzing this circuit, so don't worry about that. Ours will be much smaller like the other two we saw before. This is one crazy circuit diagram, but again, these do get fairly complicated, especially for well, a lot of things really. So a lot of times you want to know how much current is going where. So like in this case, I want to know how much current is going through this guy, how much current is going through these guys down here, based on where my voltage sources are. And so there's going to be different currents in different locations based on all those junctions and based on all those different places that the current can go. So the way to analyze that is with Kirchhoff's laws. So he has two laws. He has a current law and a voltage law. The current law is essentially conservation of charge. So essentially, if you have some node, some junction, you have some current coming in, you have some current going out, essentially whatever comes in has to go out. So you kind of treat this as a black box or a tunnel or something, and whatever goes into the tunnel has to come out. It can't just magically disappear. So at any node, any junction, the sum of current flowing in equals the sum of current going out, or going in minus going out equals 0. However you want to phrase it, or however you want to state it mathematically, it doesn't matter. So here I have I2 going in, I3 going in, I1 going out, I4 going out. Sign convention is positive into the node, negative out of the node. So going in, I2 and I3, both positive. Going out, I1 and I4, both negative. Total of that equals 0. So that is Kirchhoff's current law. The voltage law is essentially conservation of energy. So whatever happens to the voltage has to come back to 0 essentially. So again, I'm treating my negative side as the ground as 0. I have some positive voltage, and that number, whatever it is, say it's 12 volts, has to be doing something. So this 12 volts is going to be going through, in this case, I'm going through 3 resistors, resistor 1, resistor 2, and resistor 3. Essentially, these 3 resistors, R1, R2, and R3, have to take up a certain amount of voltage. So R1 is going to take up some amount V1 of voltage, R2 is going to take up some amount V2 of voltage, and R3 is going to take up some amount V3 of voltage. Those 3 voltages that those 3 resistances take up have to equal 12. So once it gets back here, it can't have anything other than 0. So I have 12 volts coming out. This takes up a certain amount. That takes up a certain amount. That takes up a certain amount. Those 3 numbers have to add up to 12 so that it gets back to 0 on the negative side. So the way I've made this, the official Kirchhoff's voltage rule or loop rule is that the sum of electrical potential differences or voltages around any closed circuit or closed loop is 0. So closed loop, anywhere that starts and ends in the same place. So if I started at this node here, I go around, when I get back there, that's a closed loop. This will get a little more complicated in more complicated circuits. For this simple circuit, it doesn't matter really where you start. You go around and it's all going to look the same. But you can do more complicated circuits. We'll see a little later. You can do more of these. So for this particular circuit, I can only come up with one equation. That's this guy here. So I have some voltage V4, usually going from negative to positive in a battery is a positive voltage. So it doesn't really matter if you go clockwise or counterclockwise. I always go clockwise. I'm not sure if that's convention, if that's just the way I do it, but I always go clockwise. And so in this case, going clockwise from negative to positive, I add 12 volts or V4 to be general. So I'm adding V4. Then whenever I go through a resistor, going through a resistor, you always lose that voltage. So V1 is negative, V2 is negative, V3 is negative. So negative V1, negative V2, negative V3, plus V4 has added to 0. That's the loop rule for this loop. So now we're going to get into, again, these kind of more complicated circuits. So I can look at this, again, relatively simple circuit. I have a voltage source, Vs, positive on top, negative on the bottom. Has some current coming out of the positive terminal. R1 and R2. So 2 resistors in series. The current has to go through R1, has to go through R2. Then it has some voltmeter essentially. So this V1 is measuring the voltage across R1. So it's basically telling me how much voltage of this Vs that R1 is taking up. Some other voltmeter V2, again, telling me how much voltage of this Vs R2 is taking up. So based on, again, Kirchhoff's loop rule, I'm going to have that V1 and V2 have to add up to this Vs, or more officially, minus V1 minus V2 plus Vs equals 0. And then I know that due to Ohm's law, that this V1, V equals IR. So V1 is this current times R1 V2 is the same current times R2, so the same current has to go through both of them because, again, the junction rule, the current has to go through here. Whatever goes through here at this junction has to come out here. And so I have the same current in both locations. So Kirchhoff's voltage law, Vs, negative to positive, minus I times R1, that's V1, minus I times R2, that's V2. That loop rule has that up to 0. Solve that for Vs. So Vs is I times R1 plus I times R2, or I times R1 plus R2. Another way I can write that is in terms of my current. So solve for current Vs over R1 plus R2. If I turn that into kind of a Ohm's law for the entire circuit, this I is my current for the entire circuit, because again, that can't go anywhere else. So that I has to be the same for my entire circuit. My entire circuit has some driving voltage of Vs. And then what I want out of this is some equivalent voltage. So if this was some circuit, I know I have a bunch of resistors in there. I want to turn into just kind of one resistor. So I can kind of put these two guys together, R1 plus R2, and call that R equivalent. So this entire circuit has some resistance of Req. So these two resistors in series are equivalent to a single resistor of this value, Req, or you can also call it, sometimes it's called R12 for R1 and R2 put together. So these two guys in series become one guy of the equivalent voltage R12 or Req. If I have lots of these, like the previous slide had 3 in series, that's going to have R1 plus R2 plus R3. If I have a whole bunch of them, you can just add them all together. You do a similar thing for resistors in parallel. So in parallel, they're on different branches. So if you can look at Kirchhoff's laws, I have some current, I'm going to call it I0 coming out of my battery. But then when it gets to this node, it gets split. So I0 coming in, I1 goes out, and so I1 goes out down, I2 goes out to the right. So in terms of Kirchhoff's current law, I1 and I2 are not the same, but they have to add up to I0. Again, it has some voltage, V1 going through R1, has some voltage V2 going through R2. Again, I kind of want to convert this into one single resistor. So how is this equivalent to just having one single resistor? So kind of not even having this branch here and just having one resistor like we did before. The way to do that is my parallel resistance equivalent RP is 1 over R1 plus 1 over R2. More common way to write that is the reciprocal. So 1 over the equivalent resistance is 1 over all the other resistances. So 1 over R1 plus 1 over R2. So again, if you have more than one of them, end up with that equation there. We'll actually derive that in class on Tuesday, so that's why it's not there. Summary though, series resistors, equivalent resistance, just add them all together. Mainly comes from Kirchhoff's current law, that the current is the same in each resistor. So these basically come from Kirchhoff's laws and Ohm's law. Current is the same in each resistor, so you have resistors all added together for the equivalent resistance. For parallel circuits, parallel resistors, key here is that the voltage law, so voltage is the same across each resistor. Again, if we go back to this slide back here, V1 and V2 both have to equal Vs. If I take this loop, this inner loop, I have a voltage source Vs, I have this voltage V1, and that's all I have. So essentially Vs minus V1 equals 0, or Vs equals V1. Or I take the outer loop, so go all the way around. So go through Vs, go through V2. All I have is Vs and V2. So again, V2 has to equal Vs. So V1 equals Vs, V2 equals Vs. So V1 equals V2. So the voltage across each resistor is the same. That's how you get that. And that's how we get this equivalent resistance in parallel to be the reciprocals. So voltage divider is a very simple circuit. It's essentially 2 resistors in series. As we saw, 2 resistors in series are going to have 2 voltages. I'm going to have some voltage V1 and some voltage V2. If I take the loop rule, then Vs has to equal V1 plus V2. So essentially, this voltage Vs is divided between V1 and V2. So that's why it's called the voltage divider. It takes that voltage and some of it goes to R1, some of it goes to R2. It kind of divides it between the two. So looking at this, so this R2, this voltage across R2 is sometimes called the output voltage because sometimes we attach some other part of the circuit to this. Like this here, I've attached a new resistor to it. So R2 is my output voltage. I basically put R1 here to control my output voltage. So I have some voltage Vs from a battery, but I don't want all that voltage going to this resistor RL over here. I only want some of it. I can control how much of it goes out there by placing another resistor up here, and then that's going to take away some of this voltage. And then I know that those two voltages have to be the same from the loop rule. So that's the basic operating of a voltage divider circuit. Again, essentially just two resistors, and you're using one to kind of control the voltage of the other one. So my output voltage, what is V2? Again, that's going to depend on the relative resistances of the two resistors, R1 and R2. The larger R1 is, the more voltage it's going to take out. So again, voltage is current times resistance, V equals IR. The current is the same to those two guys under no load. So because of that, the larger R1 is, the more voltage he's going to take out. So if R1 is much bigger, he's going to take out most of the voltage. Won't have very much voltage for V2. If R1 is really small, V2 is going to be fairly similar to Vs. So just doing that analysis, you can find that my total current I can find because it's Vs over the total equivalent resistance, R1 plus R2. And then if that's my current, multiply that by my resistance, that gives me V2. So the actual total voltage V2 is R2 over R1 plus R2 times whatever voltage source I have. Do the same thing for V1. Just replace 2 with 1 essentially. If I have a load, it gets a bit more complicated because now I have this series circuit, R1 going into this parallel circuit, R2 and RL. So 2 lines basically means parallel. So R2 parallel with RL means you do the parallel voltage law. So R2 parallel with RL is essentially this guy with R2 and RL. So same thing down here, I have R1 in series plus this parallel version, so whatever that parallel equivalent resistance is, gives you that voltage V2. Potentiometer, also called a pot, is a variable resistor. So again, the resistance is going to change. Usually we treat it like a resistor like this. So again, you think of this. So here's my symbol for resistor. Think of that as an actual resistor. It's an actual cylindrical metal or carbon film resistor, the beige or blue guys that we saw. So you think of that as having some length and some diameter. This moving wiper, so this little arrow kind of points where it is. You can think of that as being able to move. So remember that the resistance depends on the length. So if I have a total resistance here, say this total resistor is a 10 kilo ohm potentiometer. We'll see a lot of those in lab. If I put this moving wiper halfway, well, halfway is only going to be half the length. Half the length is going to be half the resistance. And therefore, if I put this moving wiper right in the middle, that should give me 5 kilo ohms of resistance instead of 10. So that's kind of what's happening when you're turning the knob. It's kind of just changing where this terminal is. And so that terminal changes the length. That length changes the resistance. And you can get pretty much anywhere between 0 and 10 kilo ohms, or whatever the potentiometer value is. 10 is not the only one, whatever the resistance is. You can get anywhere between 0 and that number by essentially changing the length by turning the knob. There's also a rotary type, which again act the same way. You have this wiper that kind of moves, and again essentially just changes the length. And so if you use the outer terminals, The outer terminals is the total resistance no matter what. The middle terminal is the one you're moving, so that's the one that's going to change. Potentiometer is not the only way you can change resistance. There's also rheostats. That's another way to do it. Rheostat only has 2 terminals though, so you don't have the full resistance. There's no terminal at the end. So rheostat is only from 0 to wherever you're measuring. There is no full option, whereas a potentiometer has the full option, so you can either connect it from the bottom to the middle, which is some variable value, or you connect from the bottom to the top, which is the full value, whatever it is. So that's the difference between potentiometers and rheostats. 2 terminals are 1. Sorry, 3 terminals are 2. The last thing for today is error analysis. So a lot of labs will be dealing with error and how much error do you have, how much error do you expect. So a whole error analysis is always good for any lab. So there's a full handout of this posted on Canvas. You should read that. Some highlights will be given here, and then some examples again will be given on Tuesday. So when we say error, we mean the difference between the measured value and the true value. Relative error, so relative to what the true value is, kind of a percent error. So the true value minus the measured error, that's your kind of actual error, that's how much you're off by. And then turning it into a percent, you divide that by the true value and multiply by 100. Oftentimes the true value is impossible to know. You're doing an experiment because you want to know what the value is. If you already know what the value is, what's the point of doing the experiment? You already know the value. So a lot of times the true value you don't really know, but sometimes there's kind of an accepted value you can use. Sometimes it's not always the case, but sometimes there is. And then uncertainty is the interval around which that true value is going to lie. So generally you have some like plus or minus value. So the value that I measured is this value, and then kind of plus or minus a certain amount. I think the true value lies somewhere in that range. So that's your uncertainty, where you think the true value actually lies based on your measurement. And so that's generally given by some probability density function. So generally we call U the standard uncertainty. It's some uncertainty in measuring some value X. So that's what I'm measuring is X. U is the uncertainty of that measurement. Relative uncertainty, I'm just dividing by what I measured. So again, kind of like I'm dividing by the true value here. Relative uncertainty, I'm dividing by the true value again. That's going to have no units because again, your uncertainty is in the same units of whatever you're measuring. So I'm measuring something in meters. My uncertainty is also in meters. If I divide by meters, then I have no units. Kind of same thing up here. This is unitless to give me a percent. And then accuracy versus precision. So accuracy is essentially how close am I to the actual value. If you think of a dartboard, accuracy is dartboard right in the middle is where you're aiming for. So right in the middle is what you want to get. If I have an accurate measurement, then all my measurements are close to that middle. Precision is essentially how small my uncertainty range is. So if the smaller uncertainty range, the more precise my measurement is. Doesn't necessarily mean it's accurate because I could have a small range, but my numbers could be off. So a lot like this dartboard over here, I have a very small uncertainty because all my measurements are hitting this area over here. But even though that gives me a very small uncertainty, if I have all these measurements, I'm going to say the true value is around here somewhere, but the true value is not around here. The true value is over there in the middle. So those are precise measurements. They're small uncertainty range, but not very accurate, unfortunately. You can also do it kind of with your kind of probability density function kind of measurement. So accuracy is, okay, here's the number I want to hit. Based on my probability density, here's the number I did hit. So the accuracy, again, is how far off I am. Precision is really how wide this distribution is. So this distribution could be the width it has here, or it could be really big. If it's really big, the precision is going to be a really big number. So again, that's kind of the difference between accuracy and precision. Repeatability versus reproducibility. So repeatability is how close you get for repeated measurements for the same measurand and the same conditions. So same procedures, same observers, same instruments, same location. Repetition, small period of time, so not much else changes, no temperature changes, nothing of that nature. So that's repeatability. Reproducibility is essentially if someone else can do it, or if you can do it under different conditions. So to determine uncertainty, have to make an assumption about the type of probability density function. So measurement type, analog measurement types usually have a triangular distribution function, and reasons for that are explained in the handout. Digital is usually rectangular. Repeated measurements, usually Gaussian. So that's just kind of basic statistics to get those. Here, my uncertainty equations, A is the difference between the largest and smallest values of my measurements, and N is the total number of measurements. So a lot of times, uncertainty depends on more than one thing. So if you have multiple sources of uncertainty, you have to be able to combine those uncertainties to give you kind of an overall uncertainty. And the way you do that is generally by counting the root mean squares, so taking the square root of the squares of all the other uncertainties. So however many uncertainties you have, square them all, add them all together, take the overall square root, and that's your total combined uncertainty. So a lot of sources of this, you have some zero errors. So a lot of times your instrument's not necessarily calibrated exactly to zero. You have some instrument uncertainty, so the instrument itself can only measure to some precision, so some uncertainty there. You have multiple measurements of the same thing. We'll see an example of that in class. One thing that does not go into this uncertainty is human error. If you make a mistake, don't just say, oh, I made a mistake and it's worth this amount of meters or whatever. If you made a mistake, go back and fix it and do the lab properly. So that is never a source of error that you should be stating. And then finally, propagation of uncertainty. So a lot of times you do a measurement, you have some uncertainty, so I measure this thing, it's this value plus or minus this number, but then you have to do a calculation with those numbers. And so when you do your calculation, obviously whatever you get out of that calculation is going to have some uncertainty as well. And so how do you then calculate the uncertainty in that new value that you calculated? So those are data reduction equations. So I have some function that I'm trying to calculate, f, and it's a function of all these parameters, x, y, z, whatever it is, and all these parameters, x, y, z, whatever they are, have some uncertainties. So there's uncertainty in delta x, sorry, there's uncertainty in x called delta x. So x is some number plus or minus some other number. So there's your x plus or minus delta x. Same thing for y, same thing for z. And so to get the error in my calculation, so to get the number itself, I just plug it into the equation, whatever the equation is, that's going to give me my number. So I use x, y, and z to give you my number. But then my error is going to depend on the other errors, the error in x, the error in y, and the error in z. And the way to do that is by taking the partial derivative of this function. So whatever the equation is, take the partial derivative of it with respect to x, multiply it by the uncertainty. That's your first term. Take your equation, whatever it is, partial derivative with respect to the second variable, or y, multiplied by that y uncertainty. Same thing for z, same thing for anything else. Again, like the previous slide, square all those, take the square root, and that's your total uncertainty. So that is it for today, the theory for today. we will see examples of that on Tuesday. So I will see you then.